Okay, so what do we do with this? Any idea?
14 to the 1/3 power.
Okay, right. So when we want to rewrite this, let's make sure we understand all the vocabulary here. So if we want to rewrite this using a rational exponent, well, what's a rational exponent?
An integer.
No, what's in general a rational number is a number that can be written as a fraction, right?
Right.
So we want to rewrite this using a rational number for our exponent. In other words, a fractional exponent. A rational exponent equals a fractional exponent. Okay, so do we know how to do this?
14 to the 1/3.
Okay, it is 14 to the 1/3, but raise your hand if you knew that, if you saw that in Algebra 1. Okay, nobody. You just saw it because you were in a class that was talking about it, I think, right? So let's talk about why that is, like what the math is here. So there's something that we can do that's very useful, and this is it. We can, if we want to ever write a radical, so let's say we're going to take the nth root, where n is just some number, right? Could be a 2, could be a 3, whatever, of something. Think of it as a number. A is the number. If n is 2, then that would be a second root. That's just a square root, right? If n is 3, then it's a cube root. If n is 4, then it's a fourth root, etc., right? If I ever want to write that as a rational exponent, I can do it this way. I can say that it's equal to a to the power of 1 over n. So whatever the index of the radical is, the number that sits on the radical, that's the denominator of the fraction. Okay, this is useful for many reasons, but one way it's useful, just practically speaking, is like a lot of times in the future you're going to want to do things like, for some reason, you're going to want to take a fifth root of 9 or something, right? So if I want to know what the fifth root of 9 is, even if I have a calculator, that's hard to find on a calculator. Right? There is no fifth root, but there is typically a way on a calculator where you can turn something into it. I mean, like you can enter numbers in a certain order and it means fifth root, but it's hard for me to do. I always look at it and I wonder what's the order I'm supposed to push the buttons. I never am sure if I'm doing it correctly. So you'll probably be in the same boat. So what I can do every time though on a calculator that's really easy is I can just take 9 to the power of 1/5. That's pretty simple to do, right? That's the same thing like on a calculator here. I could just go, on this one, I could just go 9 to the 1 divided by 5, and that's the answer. What, and 1/5 as a decimal is what?
Isn't it as a fraction?
As a decimal, what's 1/5?
1.5.
No.
What's that?
No. As a decimal, 1/5 is how many tenths? 1/5 is 2 tenths, right? If I multiply top and bottom by 2. So 1/5 is 2 tenths. So I could even say 9 to the 0.2, same answer. But that's pretty quick and easy, right? If I want to take a fifth root. I don't have to make it a decimal. You just can if you want, right? So that always works, okay? So then what's the answer going to be to this? If I want to take the cube root of 14 and I want to write that as a fractional exponent, what do I get? 14 is the base, right? Hey Brandon, why don't you get rid of those, please? Thank you. 14 to what power?
1/3.
To the 1/3. That's it. Okay? Thank you. Oh, he's gone. I don't know. I'm not sure he went. I think he went down to Cooley. Okay. Yeah. Okay. So what about this one though? This is gonna be a little different. Right now, the next example. We want to rewrite the 11th root, or excuse me, the 7th root of 11 to the 8th power.
Distribute.
I mean, not exactly. Let's talk about it. So let's go back to this other page and let's go one step further with this. So what if I want to do, instead of limiting ourselves to just one example with numbers, let's be general and let's use symbols, right, instead. So that'd be like saying, for example, what's the nth root? Let's say, what's the nth root of a to the m, how about? Okay. Well, what's the nth root of 8? We already decided what that was. The nth root of a, that's what's inside the parentheses. If I change that into a fractional exponent, what do I get in the parentheses? A to the power of 1 over n, right? So this is equal to, inside the parentheses, I'm just going to get an a to the 1 over n, and then the whole thing is going to be raised to the power of m.
So then
Now,
would you,
Go ahead, what would I do?
like, write out A over 1 and A over 1 and distribute like that?
Okay, so yeah, what do we do here? Now, you guys know the answer to this, because one of the reasons that we do this, one of the reasons that we're learning how to rewrite radicals as rational exponents or fractional exponents is because all of the PT. One of the things we can do is all those properties of exponents that we practiced back at the beginning of, what was that, module 5, I think, back at the beginning of module 5, those still work. At the time, we used nice, convenient integers for our powers, for our exponents, but now we're going to use fractions, but all the same stuff still applies. So what was my rule? If I want to do something like, let's say I want to take 2 cubed to the 4th power, well, that's equal to 2 to what power? To the 12th. Because we always said, right, if you take a power to a power, you multiply the exponents, right?
So you just do m times 1, right?
Exactly. And what's m times 1 over n?
Wouldn't it be,
How do you multiply fractions? You just multiply straight across, right?
I would say
What's
you
3
put a
times
1
1 half?
You put a 1 under the n.
Right. What's 3 times 1 half?
Oh,
1/6.
No.
Sorry, what
3
the-
times 1 half is, yeah, right, which is 3 halves, right? Same kind of thing. So I'm just going to multiply. That would be 2 to the 12th. So in this case, that's like m over 1, right? So when I multiply these, I'm just going to get a to the 1 over n times m over 1. That's just m over n, right? Okay? How about that? Okay, so we could also do this. Let's look at this slightly different way. What if we took the same idea, but this time we're going to write it as the nth root of a to the m, where the m is inside the radical.
You can't do anything.
I can. Now, whatever's inside the radical, whatever I'm taking the nth root of, is being taken to the 1 over n power, correct? So whatever's in there, call it hand. Hand is being taken to the 1 over n power. Well, hand is a to the m, right? Either way, I'm going to get a to the m times 1 over n, which is that, right? So what's the moral of the story? Whenever I'm doing something like either one of these things, whatever the type of radical it is, meaning the number associated with the radical, the index of the radical always goes where in the fraction? Bottom. Good. Whatever we're taking the base to, whatever power we're taking it to, whether it's inside the radical or outside, doesn't matter, where does that go? Top, goes in the numerator, right? So something like this then. What are we going to get for this one, Bailey? What are we going to get here if I take the 7th root of 11 to the 8th? 11 is the base, right? What's the fraction going to be? 8 over 7, good, right? Because the 7 has to go down and that has to go up.
And so
Right.
that cancels out the radical too.
Okay, so there's something that's kind of handy about this. If I want to, a lot of these questions that we're going to look at today, are going to ask you to write your answer with minimal radicands. Okay, what's a radical? All these big words I'm throwing at you. This is all stuff, don't panic. This is all stuff that we've talked about, but I've just never attached these words in the past. We don't really need to. But a radicand is just a fancy math word, and a radicand just means whatever is inside the radical is called the radicand. So if it's inside, it's a radicand. If it's outside, it's not, right? So if we want to write it with minimal radicands, that would be a problem like this. What if we had the square root of 12, and I want to simplify that? What we said, instead of using the fancy words minimal radicand, we always said in the past, if I want to simplify a square root, we want to get as much out of the square root as possible, right? Everybody agree? So how would I do that here?
You're just
we'll look at some of these in a second. We might as well do one now, kind of get the feel for this. So, in order to get something out of the square root, we used that blue chart, right? What did we do with it?
Did you use one that was symmetric?
We wanted to find the biggest perfect square factor of 12, right? We wanted to find the biggest perfect square that divides evenly into 12. So is 12 a perfect square?
Well, yeah.
No,
No.
12 is not, right? 12 is not on our list. Nothing squared, no integer squared equals 12. But if I look at the list here then, remember what we said. Half of 12 is 6, so I could jump clear down to 6 is where I'd start looking. Well, 6 is between 9, there's only one possibility, right? Only one perfect square is small enough to divide evenly into 12, and that's 4. But it does, doesn't it? Remember this stuff? So we wrote that as the square root of 4 times the square root of 3. And we always put a circle around the square root of 4. How come?
Because it's a square root.
Because it's a perfect square, right? So what is the square root of 4?
2.
2. So that's going to get out of the radical, and we're stuck with a 3 inside. We didn't get rid of it completely, but we have a minimal radicand now, because it can't go any further, right? There's no perfect square factor of 3, right? So we're going to be doing stuff like that. Well, one thing that's really nice about these fractional exponents is if we write this, so this is another way we could write this is, we could write this as the 7th root of 11 to the 8th, right? Well, what's 11 to the 8th? It's a big number. Here's what it is.
That's 100.
It's
Oh,
that.
sorry.
Okay, so this is equal to,
That's wrong.
Yeah.
That's 100.
oh, no, that's a little too big, isn't it? Yeah. 11 to the 8th. Okay, it's still pretty big. So it's the 7th root of 2, 1, 4, 3, 5, 8, 8, 8, 1. I don't know about you, but I don't really feel like doing that problem. Finding the biggest perfect 7th that divides into that number, no thank you, right? There's a lot of numbers to try. Okay, but we don't have to. Here's why we don't have to. Because if this is equal to 11 to the 8 sevenths, well, think what that means, 11 to the 8 sevenths. What is 8 sevenths as a mixed number? This is a great trick. It's not in any of the books. You gotta really watch this one. This is a good one. 11 to the 8 sevenths. What is 8 sevenths as a mixed number? 1 and 1/7, right? So we don't write things that way anymore. It's a dorky way to write numbers. That was kind of like an elementary school, maybe middle school thing. But if we write 1 and 1/7, it's now when we look at it, being in a modern, kind of a higher level math class, that looks like 1 times 1/7, right? Doesn't it? If you put two numbers next to each other, they look like they're being multiplied, right? So they're not being multiplied. What are they, when I say 1 and 1/7, how are they joined?
Addition.
Addition. Yeah, it's 1 plus an additional 1/7, right? So if I think of this as a mixed number and I write it properly as 1 plus 1/7, think what that means, 11 to the 1 plus 1/7. Think back to our properties of exponents. Ariel, what happens if I multiply a to the m times a to the n? What's that equal to? When I multiply like bases, what do I do?
I don't know.
You remember?
It's like A plus.
That's it, a plus
A
b.
plus B.
Exactly. Well, it's m plus n, right?
Yeah.
You add, is that what you're going to say? So when we multiply like bases, we add the exponents, right? So that's equal to a to the m plus n, right? Well, we can go both ways with that. If I had for some reason, if I had a to the power of m plus n, I could rewrite that as a to the m times a to the n, right? So if I have 11 to the 1 plus 1/7, how could I write that as a product of bases? It's what? 11 to the 1 times 11 to the 1/7. Well, 11 to the 1/7 is the 7th root of 11, isn't it? Right?
It just goes back to 11, 8, or 7. Doesn't it?
But now it looks like that, right? I've got 11 to the 1, which is just 11 times, wouldn't you agree that the 11 to the 1/7 written as a radical is the 7th root of 11? Okay, so that's the answer to that horrific problem right there, is this is equal to 11 times the 7th root of 11, right?
Well,
That's a lot better to do it that way than have to do it, right? See what I'm saying? So if we write something in terms of a fractional exponent, that's very helpful, because then it allows us to easily minimize the radicand, right? We'll do another one.
Can we do an assignment how to go back to mixed numbers? Because I don't remember how to do that.
Well, okay, mixed number. All you're doing, if we want to find out what 8/7 is, we just ask the question. Here's all you have to do. How many times does 7 divide into 8? 1, with how much left over?
7.
Well,
Oh,
7
wait.
goes into 8 with what remainder?
1.
1. 1/7. So real quick, what's 22/3 as a mixed number?
22, 3. That goes in there 7 times.
7 times with what left over?
1/3. Okay.
That's
I
it.
got you, man.
Okay, that's it. No big deal. Okay, so let's try one more of those. What if we had one like this? The cube root of 7 to the 5th. Yeah, you bet. If I were to take 7 to the 5th and expand that out, it's this big ugly number, right? Okay, but if I want to minimize that radicand, and I know that the number inside is 7 to the 5th, I could just turn that into a fractional exponent. What's the fractional exponent going to be?
7 to the 5th times
Or 5
7 to the 5
over 3.
over 3. As a mixed number, what is that?
This 1. Oh, what?
7 to the
Oh,
1
1.
plus
2 over 3.
2/3, exactly. And so I would say you can even skip this middle step and you can just go right over to here. You know that you're going to get 7 to the 1 and 2/3, right? You don't have to probably write it as 1 plus 2/3. You just know you're going to get 7 to that power times 7 to that power, right? Does that make sense? And then that becomes what, Brandon? 7 to the 1 is what? 7. And how do we write 7 to the 2/3? As a radical. Which part goes, so you fill in the blanks. The 7 goes there, right? What goes there? The 3, the one on the bottom does, right? So the 3 goes there and the 2 goes there, right? Well, what's 7 squared? 49. So my final answer is just 7 times the cube root of 49. That saves you a ton of time, right? So that's one of the many ways that if you take these radicals and write them as fractional exponents, it can make the math a ton easier, right? Okay, so let's go back and let's just get a couple more practices here. So let's do the opposite. This is no big deal. If I want to write 3 to the 1/3 as a,
Maybe 3 with the 3
Cube root.
okay, so yeah, what's that going to be as a radical?
3.
So the 3 goes inside,
And
Right.
3 goes on the outside on top of the little thing.
there you go, right? Because the denominator of the fraction goes on the radical, right? And inside I've got 3 to the 1, which is just 3, right? Okay, what about this one? What's 30 to the 9/7? Now let's be tricky about this and go ahead, what's it gonna be?
Okay, so the 7 goes on the radical,
Okay,
and then the 3 goes in the radical with the 9 as an exponent.
okay, good. Now if I wanna write that with minimal radicands, I could even start here and I could say, okay, 9/7 is an improper fraction, right? As a mixed number, it's bigger than 1, and so let's use that to our advantage. What is 9/7 as a mixed number?
1, 2, 7.
1 and 2/7. So I get 30 to the 1 times 30 to the 2/7, right? So what's that? Caitlin, what's that going to be if I write that?
Oh, okay.
What's that going to convert to? 30 times. Okay, good. 7th root of 30 to the 2. What is 30 squared?
30 squared?
No, it's
64.
easy, you can do it.
640.
640, yeah.
No, 30 squared.
Just kidding.
Lazy.
Okay. It's 900. There it, oh, there, how'd you get it?
3 times
3 times 3 is 9, and how many zeros?
900.
Wait, what'd she say?
900, that's right. Good job, right? Good job.
Good job, Gene.
30 times 30, we know that we're just gonna get 9, right?
I was like,
3 times 3 is 9, and I get 1, 2 zeros, and that's how we can do that one really quickly, right? So this is just equal to 30 times the 7th root of 900 if I want to be really tricky about it, right? And minimize the radicand. Okay, good, good. So you guys are getting this stuff. I mean, it's making sense. I mean, really, once you get that little trick of converting radicals to fractional exponents, you get so much additional power with that, right? No pun intended. So, how about this one? Okay. This is one we could have done back in module 3. In fact, we probably did this exact problem at some point, I guarantee, in
Would you
module
find the
3.
square?
Yeah,
Yeah, so 1313 is 164.
169,
Oh,
okay.
that's not close enough.
Okay, but yeah, so let's look at this. We need to know what's the biggest perfect square factor of 288. Is 288 a perfect square?
No.
It's not. We know it's not because if you memorized your perfect squares, which I had you memorize, remember, what's that? Or you can look up here. That doesn't go far enough though. If we go a little further, 16 squared is 256, and so we miss it, don't we? Right? 14 squared is a lot bigger than 288, so it is not a perfect square, right? So all we have to do then, remember our rule. If the integrand is not a perfect square, then we'll just start our search at half of it, right? And go down from there. Well, what's half of 288? Oh, bingo. Right
Yeah,
there.
I just said
Right?
144.
I know, that's good.
Thank you.
Yeah, that's good.
He needs all the credit.
You were so far ahead that I just caught up with you. That's good. Okay, so
That's what I'm not sure.
square root of 288 then we can rewrite as the square root of 144 times the square root of 2. I'll put a circle around that because what's the square root of 144? 12. Good. So we end up with 12 radical 2 is our answer, right? Okay, good.
Wait.
Okay, let's try another one of these. Okay, what about this? Whoa, whoa.
Oh,
Wait,
okay.
Witness.
Oh, but it doesn't.
Okay, now we gotta this is where I really like my 7th grade class, because you guys are gonna be able to take this and go, you're gonna be able to take the stuff that we did with square roots and just extrapolate your thinking, right? You're just gonna extend your thinking to a cube root. It's the same concept, right? So let's think about this now. Let's not jump into this. Don't be hasty. The cube root of 80. Instead of looking for the biggest perfect square factor of 80,
Looking for the biggest cube.
we're looking for the biggest perfect cube factor, right? Now I know that sounds hard. It sounds harder to do perfect cubes than perfect squares, but I'm going to claim that it's easier. It's easier because there are fewer of them. They grow so much faster. Let's make a list here of perfect cubes. What's 2 cubed?
8.
What's 3 cubed?
27.
Look how fast they grow. Way faster, right? What's 4 cubed?
64.
64. We're already
Ooh. 5 cubed is 125.
125.
6 cubed is 216.
Very good. Nice. She's got it. Good
I know
stuff.
my cubes,
I like
know
it.
my squares.
Yeah. Okay, so we already see that 80 is not on that list, right? And half of 80 is 40. So we'll just start, we can already cross those guys out, right? Does 27 go into 80? No, right? Does 8? It does, right? Okay, so then all we got to do, we know that 8 is a perfect square factor, and the cube root of 8 is 2. Okay, so we could rewrite this as the cube root of 8, put a circle around it, times the cube root of what? 10, because 8 times 10 is 80, right? So what's our answer? This is the one we put a circle around it because it's, what's 2? Cube root of 8 is 2, right? Because it's on our list. So we get 2 times the cube root of 10, right? Now for things like, what if we were doing, I don't think I'm going to give you a whole bunch of these to do, but I just want to make a point here.
Oh, wait.
What if we were going to do, want me to go up?
No, I just had a problem, but I figured it out.
Okay. So what if we were gonna do something like, we were gonna do a perfect, like a sixth root of some number? That sounds terrible, but sixth roots, I wanna show you something about like perfect sixth. What's 2 to the sixth? Now, how are we gonna get that? I want you guys to start, you guys are, this group, you guys are so smart. I want you to start thinking about these things. I want you to be thinking of efficient ways of doing stuff like this in your head, because that really makes you better at math and better at algebra. So one way I could do 2 to the sixth is a long way. I could say 2 times 2 is 4, times 2 is 8, times 2 is, times 2 is, times 2 is 64. So I could do it that way, right? But that's kind of time consuming and tedious.
I kind of went wrong.
Where'd I put my pen? Just had it.
It's underneath that paper, this side over here, underneath the graph.
Oh, right there, okay. Trying to get away. Okay, so it's 64, right? What's another way I could do this? Let's be really smart about our properties of exponents. What do you think?
Could you do like 2 squared?
Okay, good. I could do 2 squared to what power?
2 cubed.
To the what power? To be 2, yeah, cubed, exactly. How about that? So I could also do 4 cubed, right? Which is 64. Or, maybe even easier, I could do 2 cubed squared, right? So that's just 8 squared is 64, right? See what I'm saying? Makes it a lot easier, doesn't it? Okay, so if we continue with that list, it gets ugly pretty fast, right? 3 to the sixth, man, the only way I can think of to do that one would be like 3 to the sixth is going to be a lot of multiplying. How could I do Maisie's trick on this? I could make that 3 to 3 squared cubed. So that's just 9 cubed. What's 9 cubed? Quick.
9 cubed.
8. No, that's squared.
I don't know.
21, 1.
No.
No.
Too long. 729. It's on our list.
No, what? You need to make a cubed list, alright?
I think I did.
Alright.
Well, it ain't there.
Oh, it's not there. But I gave. Remember we had that assignment. You guys learned all those.
Yeah, probably wasn't here.
So that's it. Look how fast that grew. 729. My goodness, that's huge. Okay, now what if we do 4 to the sixth? 4 to the sixth. That'd be like saying 4 squared cubed. 16 cubed. 16 squared is 256, right? Times 16. Man, what's that gonna be? That's like 4 times 4. 4 times 256 is 1,024. 4 times that is 4,096. Yeah. How'd you get that so fast? That's good.
Because like I did 4 cubed and then I times that by 4. So I was just.
Ah, good thinking. You got good numbers. That's good. Ooh, man, you'd be a mathematician. If you can do that in your head, that's good science. So 4,000, look how fast that grew. So do you see my point now? If I have something like, even if I had you simplify something crazy like the 6th root of, how about like 256? Well, I mean, there's only one number that you could possibly even look at, which would be 64, right? You don't have to go through a whole list of them. There's just one, because they grow so fast, right? See my point? Okay. Moving on.
That's too big.
No, it's not. Try that one. Try that one. You can do that.
375, 1 over 3.
Okay, true. Okay, but can we find I want you to find the biggest perfect cube factor of 375. Let's go back to our, well, I'll make our list again.
Is it?
How about kids?
Can you just make a cube chart?
I need to, don't I?
Thank you.
Somebody want to take that off my plate? Somebody want to make a cube chart for here?
I'll do it.
Nice, thank you.
You know what? Stop.
I think you're better than Mrs. Rudolph's hers.
I'll make it. I'll just copy freaking Wilson's.
Did you do or you don't?
Wilson's is great. Like it has the base and it has square cubes.
Oh, that would be awesome. Be awesome. I'd
I'll
like
cut
that.
it out when I glue it and I'll put it
I
to
would
the wall.
love
I'll
that.
super glue it to the wall so
Oh.
you don't lose it.
Yeah, so you don't lose it.
I love it. All right.
I don't know what that was.
Yeah, I don't know either. It looked like the right thing to do. Okay, what about this? All right. What do we got here?
Yeah.
What are we gonna do with this?
I don't know.
Which one goes in? What's the biggest one that goes in?
Well, it's obviously not one of those.
Well, yeah, it is, look. So 343 doesn't work, right? What's half of 375? That's
Between
like,
6 and 5.
that's a little less than 200, right? So we know that's gonna be the line, that's the half line goes in there. Does one of those go into 375?
What? What's
125 does, right? 125 times 3,
Yeah.
right?
Yeah.
Okay?
They can.
Yes.
Shut up, Scale.
What's the cube root of 125?
5.
5.
Woo!
There it is, right? No big deal. Okay? All right, next issue. I'm gonna skip that. Okay, what about this? Last thing I wanna do, we'll end for today.
You divide, okay?
Okay, yeah, but now hold on here. This is one, we did stuff like this in module 3. This might be a little bit bigger problem than we did in module 3, but we can do this, right? Okay, think what the instructions are saying. Everybody, we got one more problem, then we're done. Right, so everybody
Okay,
bear
so
with me for this
You
one.
do the exact same thing, but you just do it separately, one for the 7, one
Ah,
for the
okay.
2016, and then you get the whole numbers, and then 2 guys.
Okay, good. Okay, so one thing we gotta do is we have to have minimal radicand. So we've gotta do the stuff we just did, right? The square root of 216 is a big ugly number, but we can make that smaller, right? We can make that look a lot better. We can simplify, hopefully simplify that radical. So on the top, we're stuck with the square root of 7's prime. There's no factor of 7, right? But what about 216? Let's look at our list. 216 is not a perfect square. Half of 216 is 108. So
Well,
we're
it's
just
a
going to
perfect
start there and
cube.
go up.
It's 6.
So what's it going to be? Does 100 go into
You
216?
get 108.
No. Does 81? No.
Half of
64?
216?
I don't think so. Does it? No.
Are you asking for the
Yes.
half of
It would,
216?
because-
Does.
108.
No, it doesn't.
No.
It doesn't.
Oh.
49?
It doesn't.
No. 36?
Yes.
No.
6 times.
Does it? I think it
6 times,
does.
I just did it on the calculator.
What is it?
6 times.
6 times. Okay. Yeah, good. Thank you.
6 to the 6.
Okay.
Get a bill.
Okay, so 216 is 36 times 6, you said, right? Somebody? Okay.
Yeah.
So we could rewrite this on the bottom. We could write the square root of 216 as the square root of 36 times the square root of 6, because 36 times 6 is 216, and 36 is a perfect square. So why do we circle it? What's it equal to? 6. Okay, so we end up with the square root of 7 over 6 times the square root of 6. Okay, now what though? We did this before. We never talked about this as rational, well maybe we did, but I don't think I said it very much. Rationalizing denominators. But what that means, what we always said was, we can't have a stranded radical in the bottom,
Did you
right?
do some one thing?
Ah, what did we do? What was our
Forgot.
trick? We gotta remind ourselves.
Take it to the top and then you square it.
Okay, yeah, there's something we did here. Now let's think about
Did you
this.
switch 6 and 7?
No. Hold up for 1 second. So what we're gonna do, now we gotta think about, let's go back to basics for a second. I just want you to think about this logically in terms of just basic math concepts that we talked about. Going clear back to the beginning of the year. Now, I don't wanna change the value of this. Everybody, please listen real quick here. This is you gotta really focus on this. If I put this in a calculator, I'm gonna get some decimal answer, agreed? Okay, and we'll have to round it, but we'll get some decimal answer. When I'm done, if I put it in a calculator, should that decimal be the same? Yeah, it better be, right? Because all we're trying to do is just write this in a simpler form. The value needs to stay the same. It's equivalent to like changing decimals to fractions or something. The numbers stay the same, but just the way it's written is different, right? Okay, so we can't change it. We can't change the value, we have to just change the way it's written. So what are the things we can do? What's our available toolkit for something like that in math? We can't square it, because if I square it, it's gonna change the value. If I take some random decimal number and square it, it's gonna be a different number, right? That doesn't work. That's not gonna work, because that changes the value. I could add 0, but that doesn't help me. Or I could multiply by 1. That does help me. How?
Wait, Oh, no, that's with imaginary numbers, never mind.
Now, if I multiply by 1, I don't have to just write it as 1. 1, anytime I write a fraction that has the same thing on the top and the bottom, that's equal to 1, isn't it? So that's a tricky way of multiplying by 1 in math. Now, what do I need to multiply by on the bottom to get rid of the radical? Because I'll just multiply the same thing on the top then. Square root of? No. 6 is the answer.
Because it cancels.
Here's why. Now, look what, my 6 is already taken care of, but what is the square root of 6 times the square root of 6?
Square root.
No, come on. It's the square root of 36, which is 6, exactly. In fact,
Oh.
that's always true, remember. It's been a while since we did this. But anytime you multiply a square root by itself, it cancels the square root. Because isn't that really just squaring it? And squaring cancels the square root, right? So on the bottom, look what I'm going to get. I'm going to get 6 times 6, which is what?
36.
Okay, on the top, sure, on the top I have to multiply that by the square root of 6 also. But what's the square root of 7 times the square root of 6? That's the square root of
42.
42. Yeah. So there's my answer. How about that? Okay. How about that? All right.
Catch me outside.
Yeah. Oh, yes. You need to get your own pizza.